Algebra 2, lesson 19, which is the inverse relationship between logarithmic and exponential functions. Let's talk about this word really quick, though. Let's just start with inverse operations. Undoing operations, sort of like if we had the number 10 and we multiply it by 5, and then we do the inverse operation, and we get our original function back. Okay, same with addition and subtraction. I can add 5, then I can do the inverse operation of that, which is subtract 5, and get my number back. So these are all operations. You learned those when you were really, really young, and they are inverse of each other. So plus and minus are inverse of each other. Multiplication and division are inverse of each other. What else? In geometry, we learned about rotations, about a point. So if we take a triangle and I rotate it 30 degrees counterclockwise, it's, this is still the same triangle, but it's over here now. Let's see if I can do that. Something like that. I can do the inverse operation and go back, and it would be back to the original triangle, right? So in this lesson, we're going to study functions that undo other functions. So given a function, f, sometimes there is another function g, so that y equals f of x, then g of y equals x. Okay, inverse functions. Sometimes when we apply these functions in succession, doing f and then g on x, the composition returns the original value x. It's like the inverse operations. We would get the original value if we did the operation and then the inverse operation, right? For that example, such a function g is called the inverse of a function f. Just like division is the inverse operation of multiplication. Okay, if you're thoroughly confused, don't worry, we're learning. If you remember, when you first learned about functions, you learned about mapping the functions. The domain is the input, the range is the output. If you talk about a function machine, you input the domain, it crunches its numbers, it does what it needs to do, and the range comes out. So let's just do an example here. Consider the mapping diagram of the function f below. Fill in the blanks of the mapping diagram of g to construct a function that undoes each output value of f. So it undoes the output value of f by returning it to the original input value of f. Domain is your input, range is your output. So let's look at this. The first one has been done for you. So we're just looking at what undoes to get us back to the beginning. The beginning being, in this case, 4. So -2 goes to, -2 goes to 4. 3 goes where? 3 goes to 1. 8, where does it go? 8 goes to 3. It's really that simple. 9 goes where? Well, 9 goes to 5. And then 15 goes to 2. Right, the set of input-output pairs for the functions f and g by filling in the blanks below. F is given 1, 3, 2, 15. We did 1. Let's do red. 1, 3, 2, 15, 3, 8, etc. So let's do G. I've got -2, 4, 3, 1, 8, 3, 9, 5, and 15, 2. Pretty simple, right? All right, so how can the points in the set G be obtained from the points in F? Well, pretty simple. Let me type it though. All right, there we go. Now I can type faster. So basically the points on G are obtained or gotten or found, whatever, from the points in F just by switching, by trading, by undoing, by switching the first entry or the first coordinate or the first ordered pair with the second entry. Second coordinate, second ordered pair, however you look at it. So if AB is a point of F, what do you think the point of G is? Yeah, BA, not capital B. I don't want a capital B. Oh, for goodness sakes. BA, and that should not be capital. That's going to bother me. I'll fix it later. Cool? All right. That's hilarious. Ha, I fixed the B. All right, next question. Peter studied the mapping diagrams of the functions f and g above and said, I can get the mapping diagram for g by simply taking the mapping diagram of f and reversing all the arrows. Is he correct? Almost. He's close. It's true, you can, let's say he can, reverse the arrows, but he also needs to switch the domain and the range labels, right? So the labels for F are just flipped for the labels for G because the input and output are also flipped. So change the labels. The labels show that the range of F is the domain of G. The domain of G is the range of F. Cool? Cool. Okay, let's do one example for discussion purposes before we get into the exercises. Let's look at two functions, f of x equals 3x and g of x equals x over 3. If you notice, 3x is my multiplication, and x over 3 is division. It's the undoing operations, right? So if I just go through a little exercise and say, okay, x, which is my input, let's just do some values, and then f of x, which it's hard for us to remember, but that's y. If I plug x in, I get negative 6, negative 3, 0, 3, and 6. Now, g of y, well, this is y. So g of y means I plug this into the equation, right? And I'm undoing everything. So negative 6 divided by 3 is negative 2. Negative 3 divided by 3 is negative 1, 0, 1, and 2. So all of these I plugged in and I calculated it. And as you can see, I undid, I reversed, I inversed, right? So when I evaluate the function f on a value of x, then the function g is the result, is the original function f. X, sorry. I evaluate this in my x, and I get f of x, which I need to say is y. Then I can take that and evaluate it and find the inverse. Okay, reverse the operation. Okay, this works on everything, right? Let's do it one more time. Okay, let's do it in the opposite way. I've got the same functions as the previous slide. I'm going to put in the same number, but I'm working in the different direction. So if I have x equals negative 2, I plug that in for g of x, and I get negative 2/3, negative 1/3, 0, 1/3, and 2/3. Now it says let y equals g of x. Now we need to find f of y. There's our function. So we're just reversing it. Negative 2/3 times 3 is negative 2. Negative 1/3 times 3 is negative 1. Negative 0 times 3 is still 0. 1/3 times 3, 2/3 times 3. Cool, so I can go back and forth no matter what. I could also graph. It's a beautiful straight line. Y equals f of x equals 3x. And y equals g of x equals x over 3. That's the graph of those two lines. I can also graph the line y equals x. And if you see, I've got a reflection. Pretty cool. As a reminder, earlier, I guess I need a full graph there, we looked at logarithmic and exponential functions. Oh, for goodness sakes. And how they are inverses of each other. So that's what we're, now I'm red, that's what we're looking at here. Okay, we have exponential functions and logarithmic functions, and how, oh, that's terrible. And how they also reflected over the line y equals x. So log functions and exponential functions are also reflections over the line y equals x. Just like our inverse functions that we just did are reflections over the line y equals x, so are exponential functions and logarithmic functions. When we first studied logs, we could go back and forth between the log function and the exponential function. I'm using random letters, I'll admit it. But those are inverses of each other. Okay, they go back and forth. We also learned that, the graphs are inverses of each other too because they reflect over the line y equals x. So we're going to set up, we're actually going to practice some procedures to find our inverse function. So let's look at this first. For each function f in the exercises 1 through 5, find the formula for the corresponding inverse function g. Graph both functions on a calculator to check your work. So the steps that we're going to work through are as follows. Let's see if I can write them down. I should probably get a different slide, but that's okay. So first we're going to write y equals f of x using what you're given. Okay? Then we're going to exchange x and y to get x equals f of y. Then we're going to solve your new equation for y in the simplest form. And now we have the formula for g. Alright, so those are our 4 steps. Let's practice them with this first one. And I'll do this with you. So first I have f of x equals 1 minus 4x. I'm going to write y equals 1 minus 4x. And I'm going to exchange my x's and y's. And then I'm going to solve for x. I know it's sort of silly. Let's see. I'm going to add 4y to both sides. Equals 1. Subtract x from both sides. And then divide everything by 4. And then rewrite it, g of x. So I now have my inverse function. I just made a mistake. I just fixed a mistake. Okay, let's graph these and show that they are inverses of each other. They should reflect over the line y equals x, right? So if you can see this, my original equation y equals 1 minus 4x is right there in red. My equation g equals 1 minus x over 4 is right there in blue. Let's erase that. Is right there in blue, and then the equation y equals x, which is my reflection line, is right here in green. So it is a reflection. Pretty cool. Okay, why don't you try this one? I'm going to push pause and see if you can work it on your own. Remember the steps on the last slide. Hopefully you wrote them down. If not, rewind. Here we are. The line y equals x is in red. Y equals x cubed minus 3 is in yellow. And the last one is our g of x. And that is in black. There we go. And this one is actually supposed to point to the function. And it looks like a reflection. That's pretty cool. Alright, a little bit harder to do, so I'll work. This is new and different. We haven't seen one like this before, so I'll work this one with you. Go through the steps, right? Change the f of x to a y. And this right here is just to prevent us from dividing by 0 or from taking the log of a 0. Not a big deal, right? So switch our x's and y's. 3 log y squared. I'm going to drop that square in front of the log and get 6 log y. Now we have logarithmic function. I need to change it to, I need to change it to exponential function. So let's see, what else can I do? I'll have log y equals x over 6, and then 10 raised to the x over 6 power equals y. That's a 6. g of x equals 10 to the x over 6. That is our inverse function. So we have our beginning and our end. And let me get a graph for you. So here we go. Not quite as nice of a picture, but I've got my g of x. Oh, there it goes. My g of x, my f of x, and the line y equals x. It's a pretty cool reflection. All right, try number 4 on your own. I bet you're going to have to take a log to solve for x, right? So go ahead and try it. All right, there's your answer. We're going to go even older school here. Oh my gosh, I hate it when that happens. Our exponential function looks something like this. Our logarithmic function, something like that. And our y equals x goes right smack dab through the middle. We had exponential function, and logarithmic function. Very cool. All right, you did great on that one. Let's try again. I'm going to push pause. Okay, that one had a few more steps, but very doable. Our graphs look pretty exponential again. See if I can sketch it for you real quick. We'll do that in red. That is my f of x. About like that. And in yellow, and you can always get decimals out to graph this. A little bit like that. And then our graph y equals x goes right there. Cool. All right, let's talk about it a little bit more. We have another problem. Cindy thinks that the inverse of f of x equals x minus 2 is g of x equals 2 minus x. That was sloppy. To justify her answer, she calculates f of 2 equals 0, and then substitutes 0, which is the output, into g, so g of 0 equals 2 minus 0 equals 2 to get the original input. How does that work? Well, let's try another number, right? Let's try f of 3 equals 3 minus 2, which is 1. So I should be able to put that back into here. Sorry, wrong letter. G of 1, which is 2 minus 1, is 1. So I'm supposed to get 3 back. Just like here I got 2 back. So nope, it doesn't work. Okay, it has to work for any number, not just a select few. Let's try another one. After finding the inverse for several functions, Henry claims that every function must have an inverse. Rihanna says that his statement is not true and came up with the following example. F of x equals absolute value of x has an inverse. Oh, if f of x equals absolute value of an x has an inverse, then because f of 3 equals, f of 3 and f of negative 3 both have the same output. They both are 3. The inverse function g would have to map 3 to both negative 3 and positive 3 simultaneously, which violates the definition of a function. What's another example of a function without an inverse? Well, right there that showed me that f of x equals x squared has the same issue as the absolute value of x. Doesn't have an inverse. So Last example, we've got 3 more slides. Consider the function f of x equals x2 to the x power plus 1, whose graph is shown to the right. What are the domain and range of f of x? Well, I do know that, oh, for goodness sakes, 2 to the x has a domain of all real numbers and a range that will go from 0 to infinity. So 2 to the x plus 1, nope, is going to have a domain of all real numbers and a range that changes just a little bit, goes from 1 to infinity. Sketch the graph of the inverse function g on the graph. What type of function do you expect g to be? So I know I can just reflect this. So it's going to look something like that. So what does this look like? The regular function looks like an exponential function, so I know that the inverse is going to be a log function. I mean, we know it from the look of the graph, and because if we're trying to do the inverse of an exponential function, it's going to be logarithmic. What are the domain and the range of g? So the range is going to be all real numbers, and the domain is going to be from 1 to infinity. Do you see a pattern there? I did not write these backwards. You may think so, but no, I did not. We change our input and output, right? That's how we do the inverse functions. Remember we talked about AB going to BA, and we need to change the labels, the input and the output labels also, right? Find the formula for g. So we started with f of x equals 2 to the x plus 1, and let's just go through our step. Yep, that's right. So solve for x. I've got 2 to the y equals x minus 1. Take the log of both sides. Y log 2 equals log of x minus 1. Y equals log x minus 1 over log 2. Do the backwards of the change of base formula, and I'm going to go ahead and write the g of x equals log base 2 of x minus 1, and that has to be for x greater than 1 because you can't take the log of 0. Cool? That was a little complicated, but sort of fun. That's why we did all this in the last few sections, right? Alright, sweet. Lesson summary. What did we do? Right here, this right here are the steps that we did. So therefore, and then f of x and log base b of x, and g of x, b to the x are inverses. That's the log and the exponent. Cool? Alright, nice work.